Welcome back, everybody. Sorry about last Thursday. Got out of that shower, just hit my ankle just wrong, and I guess it wasn't a lasting damage, but it's just I couldn't walk on it for the rest of the day. And next morning it was still pretty fucking sore too.
So last Thursday was your birthday?
Yeah, it's a hell of a way to spend my birthday.
It's also my sister's birthday.
Oh, neat. I hope you like your sister.
Well, because you canceled class, I got to spend more time with her on her birthday.
That doesn't mean that was a good thing.
Not
If you don't like your
necessarily.
sister, that sucks. So I'm going to assume, since you said you got to spend more time with her, rather than I had to spend more time with her, that you do like your sister. Let's take a look at doing inverse functions. Recall that for an inverse of f of x to exist, what the hell? Thank you. All right. Inverses of functions exist. Let's say function f of x exists. We can use any letter, but we're using f because that's how we roll. If f is 1 to 1, which means it passes the vertical line test and the horizontal line test. Another way they like to put in words is if A does not equal B, implies both directions that f of A does not equal f of B. So if A doesn't equal B, like the two different x values aren't the same, then the y values are different. And then if two y values are different, then two x values are different. It's a two-way street. That's when you're not doing not graphing and drawing a line. Let's take a look at some. Let's do some basic ones like, I don't know, f of x equals 4x minus 5. Any function that has an mx plus a b always passes this test, unless m can't equal 0. If m equals 0, we have a horizontal line. Other than that, it's just a line, so it's always going to pass. And the way we find the inverse is we say this equals y. And then we do the swap-a-root. We put x's where y's are and y's are where x's is. That sounds weird. And we solve for y. We get y equals 1/4 x plus 5/4. And we place y with f inverse. This is one way you could check to see if two different functions are inverses. You could literally just find the inverse and go, does it match the other one? And if it does, you're good. The other way to check for inverses, as a reminder, is if you take f of inverse and you put it into f, you just get x back. And the same with the vice versa. If you take a function f and you put it in f inverse, you get x. So 1/4 plus 5/4. That's my F inverse function. If I take f of x and put it in there. I get x minus 5/4 plus 5/4. And that does equal x. So they're inverses. That's a quick recap and reminder of what we did last week. Now I'm gonna put you guys to work. Do you have any questions? So why don't you guys try let's see. F of x equals square root of x plus 6, where x is greater than or equal to -6. Find F inverse and the new domain and range. How are we doing? Okay, so let's make sure everyone got the same F inverse first. We got y equals square root of x plus 6. And we give them the swap. And we square both sides. And we get y, which equals F inverse, is x squared minus 6. Now, it's handy to remember that the domain of F equals the range of F inverse. And the range of F is the domain of F inverse. Because the X's and Y values swap, so do the domains and ranges. So having X is greater than or equal to -6 tells me that in the new function, our inverse function, Y has to be greater than or equal to -6, because we're swapping X and Y. Now, the easiest way to figure out what to do for X here is figure out what Y does over here. If we had a restriction at -6, if I stick in -6, F of -6 was 0. And if I do something like -5, I get 1. The graph of the square root function goes like this. At -6. It actually only goes up, so the range is Y is greater than or equal to 0, which is going to translate over here to the X is greater than or equal to 0. And we could have seen that if we'd worked with this. No, we can't. Other than the graph of X squared minus 6 is this. And we need to keep it 1-to-1. So this is way F inverse is looking. It needs the domain restriction there. So we need to restrict domain to be X is greater than 0. That will get rid of this side. And now this is 1-to-1. It's going to pass the vertical line test. It's going to pass the horizontal line test. It's all a little tricky. What about F of X equals 4/X? I mean, I guess maybe we should add in X can't equal 0. I think that's a little bit obvious, but And if you recall what the graph of 1 over x looks like, 1 over x is like this. So it passes the 1-to-1 test. 4 over x just makes it a little bit steeper. Four over x, I believe, does a little bit more like this. And like that, but it's still the same thing. It actually shows us our other domain range restriction. What is the range restricted on this? What can y not equal on the graph? Y can't equal 0. That shows for in the F inverse, but we can also see that it's asymptotic along here. The two axes, the x-axis and the y-axis, are asymptotes. So x can equal y, x can equal 0 and y can equal 0, which means when we switch them for that's for F, when we do F inverse, the same event happens. Well, this now says y can't equal 0, and this one now says x can't equal 0, but they're still the same thing. What's the new function? Y equals 4 over x. We swap them. We solve for y. Not 4x, but 4 over x. Which is F inverse. But interestingly enough, it's also f of x. The 1 over x function is actually its own inverse, which is pretty cool. That's crazy. Do one more fun one. Okay, so looking at this, that x squared makes me worried that it's not going to be 1-to-1, because when we have like an x squared graph, it's not 1-to-1. So I'm going to try to graph this first. And what I'm going to do is I'm going to say f of x is y. And I'm just going to square both sides. If I square both sides, I get y squared equals x squared minus 16. And if I move that over, I get y squared or negative x squared plus y squared equals negative 16. Or if I do it the other way, x squared minus y squared equals 16. X has got to be the greater than or equal to 4. This is a hyperbola. A little bit quicker to grab on Desmos. Let's come over to Desmos. I can actually grab it the way they have it. Why is it making a fraction? And it had a negative. And we had the restriction that x was greater than or equal to 4, which gets rid of this left side. The full hyperbola is that. I think there's a way of doing x is greater than or equal to 4. Maybe it's put this in curly braces. There we go. So we can see it's 1-to-1. That's the original graph. Well, that's the whole graph. Going back to the camera. Whichever one's positive on a hyperbola on this, the x squared is positive, means the openings are in that direction. The openings are along x. Or like the little mini parabolas that are part of it. If it was y squared minus x squared, it would open upward and downward. We can see from here, we've got an x restriction of greater than or equal to 4. If I look here, if I stick in 4, I get 0 here. Right? And I can see that it's always got to be negative. This doesn't have a positive value whatsoever. So if you drew, like, dotted in the hyperbola, if you were doing this by hand and didn't have Desmos, that is kind of what gives it away. X is greater than or equal to 4. This tells me y has to be less than or equal to 0. So if I stick in 4, I get the actual 0. And then the negative sign tells me everything else has got to be lower. That's f of x. So it does have an inverse. That was what we were looking for. Let's find it. We're going to start here. And we're going to do the swap root. We square both sides. This one ends up giving us y squared equals x squared plus 16. So y equals the square root of x squared plus 16. Which is crazy. And our restrictions split. X was greater than 4, now tells me that Y needs to be greater than or equal to 4. And Y was less than 0, tells me that X now has to be less than or equal to 0. And it should actually end up looking something like this. That should be F inverse. Because if I wrote this as a hyperbola, this is y squared minus x squared equals 16. So it's the same hyperbola, but it opens up or down. Something fun about inverses, they are always reflections of each other over the y equals x line. See if we got another fun one we want to do. Yeah. Let's do one of the weird rational ones. And x cannot equal 3. If we plotted this, we could see how it looks. They have the same power, so there's a horizontal asymptote at y equals 2. We know we have a vertical asymptote at x equals 3. And the easiest way to really do it is check where 0 lies. When x equals 0, what do I have? 6 over -3 is -2. It's down here. Which means it's got to be doing something like this. So it's going to be 1 to 1. Now, go ahead and try to flip it. Find the inverse. Give me a couple more minutes. Phone in hand means you're done. All right. We swap them, right? Put my X over here and these become Y's. What's the go-to choice here? Get rid of the fraction, right? Multiply both sides by y minus 3, and we get x times y minus 3 equals 2y plus 6. Now what? That's a good choice. Always a good choice. Now what? So that was subtracting 2y and adding 3x to both sides. Yeah, that's a good choice. Why did we do that? That's true. We got all the y's together. What can we do with that? Factor. We pull out a y. I have x minus 2 left times it. And finally, x minus 2 is a coefficient. We can divide by it. Y, which equals f inverse, is 3x plus 6 over x minus 2. And you'll see we now have our vertical asymptote at x equals 2. And we have a horizontal asymptote at the coefficients is 3 over 1, y equals 3. Which is the good old swapperoo from up here. We can see that these are the opposite of what was up here. BA up here was x equals 3. HA was y equals 2. And the values have switched. Any questions? Did the exponential section make sense? This was just drafting some of them. Where we will be going in the next couple of days is this. Today, we're going to be covering logarithms. And natural logarithms, which is the same thing as log base 10 of x. And we will see over this week that e to the x And y equals natural log of x are inverse functions. So the base graph of y equals e to the x goes through 1 and comes up like that, and it has a horizontal asymptote at y equals 0. The inverse function passes through x equals 1. It has y equals 0 as a vertical asymptote, or x equals 0 as a vertical asymptote. And if I had done these well, I don't think I have looking at it. These look like mirrors of each other over the y equals x line. So today we will be covering logarithms, their properties, the math operations that work with them, because they do stuff a little differently than normal math operations. And that's 4.3. What are we doing in 4.3? Oh, exploring the change of base theorems. For logarithms, which is only helpful really in a recalculator world. We'll chill out until 3:10. You guys have any questions? Come on, folks. We'll see this stuff in, I think, 4.5. Maybe 4.6. Looking at the comparative connection between natural log or the inverse functions and e to the x. I know, let's start recording.